Okay, we're going to go ahead and get started here. Welcome to session 6 of the crustal deformation modeling tutorial. And we're going to focus in this session on running PyLith in parallel. And so this will be less technical, certainly, than the solver discussion, and less technical than most of the other sessions. We're going to go over some slides, and then I'm going to show you running in parallel on both my laptop as well as a cluster. And so let's jump right in and look at how we run PyLith in parallel and some issues related to running PyLith in parallel. And so the concepts we're going to cover in this session are running PyLith in parallel on a desktop or laptop with multiple processors and or cores. These days, most processors have multiple cores. So even if you have a single processor, you have multiple cores. And if you have multiple processors, usually you have multiple cores per processor. We'll also examine running on a cluster with multiple compute nodes. So there we may have multiple processors on a compute node and multiple cores on each of those processors. So usually now most clusters have 8 to 12 cores per compute node, and you can put in, several compute nodes, and so quickly you can get up to 100 to 200 cores of performance with, hundreds of gigabytes or more of memory. So they can be pretty powerful even with not that much hardware. We're going to look at optimizing PyLith performance to make better use of running in parallel. And on a cluster, we have to build from PyLith from source, so we'll just very briefly go over some of the issues related to building PyLith from source. And we'll spend, in terms of running on a cluster, we're going to examine using PyLith on a queue system, so on a batch queue system where you have to submit a job, wait for the job to start, the job runs, and then you're sent the results. And also look at parallel performance of PyLith. How do you tell when PyLith is running well in parallel? What things do you look for to make sure things run to completion and so forth? So how do you run PyLith in parallel, and why would you want to run PyLith in parallel? Well, certainly on a laptop or desktop, running in parallel, you're trying to reduce the amount of runtime. So instead of just using one core, running it with one process and one core, make use of the fact that you have multiple cores sitting right there on your desktop. And this is available within the binary, and all you have to do is add the command line argument -- nodes equals the number of cores. And this, I put number of cores there because generally you'd want one process per core. And so -- nodes will spawn that many processes running in parallel. And if you run more processes than you have cores, they basically end up competing for each other, and you'll run much, much slower. If you use fewer processes than number of cores, sometimes you'll actually get the same amount of performance as used all of them, as we'll see, and that's related to the memory bandwidth. On a cluster, the two main reasons you want to run on a cluster is both to reduce the runtime by distributing the floating point operations among many different compute nodes and cores, but also to run larger problems. So here on your desktop or laptop, you can't change the total amount of memory, and one process can access all of your memory. But on a cluster, you have multiple compute nodes. You then have usually twice as much memory, or n times for the number of compute nodes, times the amount of memory that you have, say, on your desktop. And so you can then run larger jobs that have access to all of that memory. So you can distribute your memory usage as well as your floating point operations. As I mentioned, running on a cluster requires building from source. And it's very important to realize that when you build from source, you have to run for the proper configuration. And on a cluster, we can't really distribute a binary that's going to work on different clusters because there's so many types of clusters out there. They're all running various versions of the message passing interfaces, which is what we use for parallel processing. And so you really need to take advantage of a cluster. You need to be building the code for that hardware. And so it really has to be done on sort of a case-by-case basis. What the greater complexity of running a cluster is, you need additional parameters for to submit to the batch queue system.
Oh, so Brad, just before you go on, do you mind if I make a brief comment? If anyone has seen the terms weak scaling and strong scaling before, the first bullet here, reduce runtime, is what people in the computer science world call strong scaling. You have a fixed problem you want to solve, and then you put more processes in to try to solve it faster. Whereas the second bullet, run larger problems, is what the computer science people call weak scaling, which is I have a certain amount of resources, and I'd like to run bigger and bigger problems. So I just wanted to make that connection for these jargon terms. Thanks.
So okay. So how does PyLith run in parallel? PyLith uses the single program, multiple data parallel processing model, where we're going to run the exact same code, but each process is going to run on its own part of the volume. So we distribute the volume, or we're actually distributing the cells and the nodes associated with those cells over the various processors. And each piece is solving the same equations, but they're solving it on their own little piece. And by sort of the communication between the processors keeps everything in sync so that we come up with the same consistent solution as if we'd ran it all on a single machine. And so the way PyLith runs is the run really starts up on process 0. We always have a process 0 even when we're running in serial, and this is a common model used in parallel processing. So process 0, it reads in the mesh. Then if there's a fault, it's going to add the cohesive cells by adjusting the mesh topology. Then it partitions the mesh and determines the vertices that are shared by multiple processes. And then it distributes the relevant portion of the mesh to each process. And at that point, the other processors come in, and there's this optional step of refining the mesh on each processor to be able to run an even larger problem. And then we really begin the simulation part, where each processor then does its initialization, and we begin solving the equations and time stepping, writing output, and so forth. And so it's important to be aware that that PyLith uses this first step of reading in the mesh by a single process, because as Matt mentioned, that really sort of controls the size of the problem that we can run now. You have to be able to fit the entire mesh, not all of the data structures associated with solving the equations, but just the mesh on a single processor or a single compute node, and be able to add the cohesive cells, partition the mesh, and send it out to the other processors. And probably in the next 5 years, this will change, or perhaps fewer, maybe 2 or 3 years, this will change, and we'll go to even more scalable approach where all the processors will read in part of the mesh, then they'll sort of do some communication to sort of sync up, maybe redivide things, redistribute things to make sure they're all even, everything's evenly distributed, and then run in parallel. So that a couple sort of running in parallel notes is when you are running in parallel, there's a couple things to point out, and your efficiency can really depend on your choice of parameters and on the hardware you're using. The first thing to note is you should not be using VTK output if you're running in parallel. The VTK output in version 1.9 writes everything out in ASCII, which is rather slow, and each process is sending its data to process 0 for writing. And so every process has to bundle up the values it wants to send into process 0, and process 0 then has to collect them, unpack them, and then write it out. HDF5 is set up to run in parallel, and that includes the binary that's on your the PyLith binary, and so even your PyLith binary can write to your local disk in parallel. And not only is it writing in binary, which is much faster than writing ASCII, but each process is writing its own data. And all of this happens behind the scenes, and so you'll end up with a single file that contains all of the information. The second is in terms of solver performance. So as Matt pointed out in the last session, in a quasi-static simulation, the field split with the algebraic multi-grid preconditioning is going to scale much, much better than additive Schwartz. So you don't want to be running additive Schwartz in parallel for decent-sized problems because it's going to take, perhaps thousands of iterations to converge. So make use of the information in the PyLith manual on the algebraic multi-grid and the concepts that Matt covered in the last tutorial using those solver 03.cfg settings, and the solver 03 was the toy problem, the solver 07 are the ones that are much more scalable. My dynamic simulations are trivial solve, scales extremely well. It's essentially embarrassing parallel because everything is decoupled at that point. So there's no issues in terms of scaling of the solve in the dynamic simulations. And we'll look at the performance, and you'll see the difference of where PyLith spends its time in the quasi-static simulations versus the dynamic simulations. The other two important points on overall performance: the speed of the memory of the system you're running on, so how fast the computer can take memory from the actual processor and take values from the processor and to and from pages of memory and those within the cache, really determines the speed at which you can do operations. And so the connection between the memory and the CPU is very important. Usually there's more memory cards on your computer, even your laptop, than there are memory buses between the memory boards and your CPU. And so usually you'll saturate at either 2 cores per process or 3, or at some fraction of the total number of cores that you have, just because as for these large problems that use a lot of memory, you basically are spending how fast you can run through all of the floating point operations you need to do at each time step is not controlled by how fast the CPU can do those operations. It's controlled by how fast you can get all of the memory where those values are stored, unpack them, unpack them to and from memory rather than actually doing the floating point operations. And you can get, on your local laptop, you may get some marginal speed improvement if you compile from source for your hardware. You can be increasing optimization and sort of doing additional tuning for your hardware. In many cases, it's probably not going to be worth your effort, but it might be if you intend to run on sort of a souped-up desktop with lots of cores. You may be able to do a little better. So running PyLith on a desktop. As I said before, all you have to do is add in the argument --nodes equals number of cores. And this works for the PyLith binary. And the PyLith binary allows inter-process communication only within a single computer. So it's set up to spawn threads on your machine, but it's not, the communication between the processes isn't allowed to go across, say, a computer network to another machine, which is how compute nodes within a cluster are connected. So it works on laptops, desktops, and you can run it on a single compute node of a cluster. But in most cases, and that's due to the fact that the MPI that runs is not really using the hardware of a cluster. It's just using what you have essentially on a normal Unix machine. Yeah, so Aaron asked, is it just as simple as doing PyLith step01.cfg -- nodes equals, and then the number of cores, say 2? And yes, that's as simple as that, and we'll take a look at that in a minute. And so the reason why I said you might get modest performance gains is that you can optimize the code for your hardware. So let's switch now and run PyLith on our desktop. So I'll just show my whole desktop. So that's not actually the terminal window I want, because I'm already logged into the cluster. So let's get a bigger screen here. Oops. There, that's good. So we're going to go to examples 3D hex 8, our old friend here. PyLith step01.cfg -- nodes equals 2. And so there it ran. I scroll up through the PyLith summary. Somewhere here it says, I ran with 2 processors. So, and you'll notice that, let's see, where down here, you'll see there's message lengths now down here in this column. So it's telling you how many messages were sent back and forth. Here's the number of messages. Here's the length of the message. So you can see that some parts are running in parallel in terms of sending information back and forth. There are some parts that don't need to send information back and forth. So they're running completely independent on each processor, doing their own thing on their part of the domain. And so I think there's some, we haven't played around with it yet. Let's see, I think there may be something. So step 21, which was our Green's function problem, has this information about the distribution. So let's run step 21, or let's do 3 cores. So I have a 4-core machine, and so what happened? Oh, there was a Green's function problem, so I forgot to tell it problem equals problems.Green's functions. So let's look at how the mesh was partitioned. So I'm going to open up, see what directory I'm in, output hex 8. I want step 21. Here's partition. So there's this partitioning profile. It has 1 value in there, partition. And so here's my partition among 3 processes. So this is, a pretty simple discretization. You'll notice that by doing 3, it had a little, you have to sort of, by doing an odd number with a nice square rectangular cube that's very regular, you're going to get sort of some irregular boundaries. And so you'll see a little bit of irregularity here. Whereas here at a nice clean sweep. I do the threshold filter over here. I can change, let's just look at process 1. So here's process 1. Then we can look here, let's go. So that's process 0. This is process 1. And then we can look at process 2. And so here's process 2. So it's not, perfect, wasn't a perfectly clean slice. But the partitioner, in this case, it's going to try and minimize the amount of communication. So it didn't, notice it didn't take 3 vertical slices. And the partitioner is going to try and minimize the area of essentially the area of contact between the 3 volumes. And so that's why it took these semi-irregular. It'll look better when we do, say, 4 processes. So let's go back. Let's delete this. Minimize that window. Let's do 4 processes. There you can see it did sort of a more what you would expect. It didn't do completely the sort of 4 vertical slices that you might expect it to do. Part of that has to do with the fact that we have a fault in there, and so it decided to actually avoid the fault a little bit. So you can see like these nodes over here on this vertical slice were put onto this process. And so that's probably why it did this sort of diagonal cut across here, because of this right here, our faults, I think this is our faults here. We're doing x positive and x minus spaces. So here's our fault right here. So I'm not quite sure why it went slightly off the diagonal, but that's what it chose to do. But it's a near optimal partition. So any questions about running in parallel on a desktop? So quite straightforward. One thing I can show you is you may be asking, well, how did it run in parallel? And so this launcher is how the run is launched or set up. And so what command it actually performed is that doing --launcher.dry is a command saying don't actually do a dry run of launching the simulation. And so what it did is it ran this command mpirun.mp4. This is the number of cores or number of processes to run. And then it was launching mpi numbasys-pyr start, and then a bunch of information, and then our command line arguments are down here. And you'll see that there's additional information about the job name, job ID, macros, number of nodes. And this is actually what PyLith, even without running in parallel, this is actually what PyLith is doing behind the scenes when you run a job. So it's actually, even when you run in serial, it's actually running the MPI command, but it's only going to launch one process. But it does all of this. When it actually starts up, it's going to do this MPI nemesis, this is running Python in parallel, and it's starting up the Pyr configuration And all this information here is related to the Python path to make sure that it is all the information about the Python. And it's telling it to, yes, don't just launch, but start up. So you generally don't need to know about launching, doing a dry run of the launcher, unless you're having trouble actually accessing the MPI. But with the binary, this won't be an issue because everything has been set up properly. So let's go back to the slides. So I'm going to stop sharing and we'll switch to